Basically, the n choose I is the coefficient, and it's u to the I, 1 minus u to the n minus I. The problem is with a surface, you have to have two variables. So we have a u variable that's in our curved direction, and we have a v variable that basically goes normal or perpendicular to our curved direction. And because we have two parameters, we need two blending functions. So we have added a u, a b, j, m, a v as our other blending function. When you expand its Bernstein polynomial, you get an m choose I or choose j as the coefficients, and then vi 1 minus v to the m minus j. There's a representation of a very simple linear surface. We have u in the curved direction. We have v in the kind of normal or perpendicular direction, going from 0 to 1. And we have 4 points now that are interpolated by the surface, meaning that they go through those points. But all of the other points that we typically see, in this case 16 points, only the corners are on the surface. So for our simple representation, we have 8 points that define our curve, and we need to kind of figure out how to lay this out. Well, the first thing that we have to do is we have to compute our coefficients. So the coefficients along the curve are 1, 3, 3, 1, just like before. This is a representation of our basis functions, our Bernstein basis functions, multiplied out. So there's the 1 minus u cubed, 3u, 1 minus u squared, 3u squared, 1 minus u, and u cubed define this curve. What we now need to do is compute the m choose j. And when we compute it, we only have 2 of them. We've only got 2 points going in that direction. So it's a linear representation. And so it's 1 and 1 are the linear coefficients. So we have 1 minus v and v. So what are we going to do with now this set of Bernstein basis that we have? Well, we have to actually expand this thing. And when we expand it out, we get our first curve, which is this top line. So it's p 0, 0 times 1 minus u cubed plus p plus 3. The p is 1 comma 0. So it's this point right here. Times u to the first, 1 minus u squared, and so on, which lays out this first curve, but we have to multiply it times 1 minus v. Why 1 minus v? Well, when v is 0, we want to be on this first curve, right? When v is 1, where do we want to be? We want to be on the second curve. So notice that if we just look at v for a second, when v is 0, this last curve blows away. When it's 0, we're just influenced by that. What if v was 0.5? We would be on a curve that is halfway through the surface, and we would actually be on the surface. Does that make sense? So what are we going to do with this expanded polynomial thing? What did we do on the curve? We wanted to get it into a representation that the computer uses, which is what? A matrix representation. So we're going to take this equation at the bottom, and we're going to quickly, we're out of time, lay it out as a curve. And the easiest way to do that is first separate out the V's. This is where we're going to pick up on Thursday. Separate out the V's, and we just have curve 0 times all of this, and curve 1 times all of it. So we've got 2 equations times that blending function, and we will end there.